is that during the session last week, we had a few questions in the chat. There were one or two that I promised to answer this week. However, on ending the Zoom session, the chat was no longer available. So I don't know which questions there were. So could you please use the chat to state those questions again so that I can go through them. Also, please add the questions or topics that you would like to get answers for today. I only looked at then the Moodle part. There's this request to go through static analysis and control flows graphs again. And there was one question about the equations for the complexity. And I think I'm going to start with that. So the question was, just a moment, do we need to memorize the different formulas for calculating software complexity like Halstead's work or McCabe's complexity? Um, Clearly, McCabe's complexity, there was an additional discussion around it. You need to be able to remember that equation because it's so simple. It's not anything that is hard to remember, and the whole discussion why McCabe is not ideal is building upon this equation and showing why that is not a good idea. Halstead, on the other side, there are only these four elements, and the computation is not that important. And I would say how exactly Halstead is computed, you don't have to remember. I hope that answers that question. There's one in the chat. Through one part D of the 2024 paper. Okay. I'm gonna start with the first question because Varun was the fastest. Just gonna recover that paper. Just a moment. Okay, I believe it is this exam that the question is about, and we discussed, I believe, C and not D. And I think that's the question that has been asked. Let me quickly check. How do I get to the chat? Well, I think that's interesting. I can't go to the chat directly from here. Oh, there it is. Um, Part 1D of the 24 program. Okay, so in addition to the four tests, we know now which ones are passing and which one is failing. So we know test 1, 2, 3 are passing and test 4 is the failing one. Assuming that the source code contains a single fault, and by only taking the data for the failing tests into account, which statements can you assume to be non-faulty? This goes back to the discussion we had last week about the assumption of containing a single fault. So we know now if we assume that there's a single fault, that single fault must be executed by all failing tests. Okay, so that means we have test 1, 2, 3 are passing and only test 4 is failing. So the fault must be executed by test 4. And the question is, which statements can you assume to be non-faulty? Therefore, statement 10, 15, 16, and 18 in this example cannot contain the fault. And the explanation would be, if there is a single fault, then all failing tests must execute that fault. Okay, so we have excluded lines 10, 15, 16, and 18 because test 4 is the failing one. I hope that answers that question. Any follow-up question to that? Okay, that doesn't seem to be the case. Now, is it fine to change the convention in Miller-Myers algorithm, like making moving up to down as insert instead of delete? I don't understand that question. Because by traversing Miller's algorithm, you are moving down in the matrix, and inversing the approach would not necessarily work unless you turn it completely around backwards. So basically transposing the matrix. Maybe you want to clarify your question. Okay, so there are two direct messages. It would probably be helpful if you're using it as a chat to everybody so that these questions are seen. The next question, therefore, is, will the software mining repositories topic be an exam? I assume not, since it's already covered in the assignment extensively. Yes, there will not be a question about mining software repositories because that has been covered extensively in the coursework. Okay, next question, again, direct. For Gradle, do we need to know anything apart from difference in building philosophy? Since slides mainly focused on this. Oh, that's a good question. So you don't need to be able to write a Gradle build script, but you need to know the differences in philosophy, and you need to know how task, target, and dependencies are arranged in Gradle. Because for the whole building part, we have extensively discussed the differences on which level dependencies are created in make and so on. And the terminology might differ between the different tools and approaches. So what is a target? What is a task? What is a dependence? Okay, the next question. One question I have is regarding how close our final paper will be to the existing papers. And if you could give us some areas worth revising more before the exam, this would really be helpful to target our revision. Okay, so let's start it with the first part. One question is how I have is regarding how close our final paper will be to the existing papers. This is the first year that we have a multiple choice question part in the beginning, which is um, not having before, but it's only worth 10 points. So yes, that's a significant difference to before. The rest, yes, there is exactly in the next part a scenario as you have seen before. And then there are these two questions about exam style questions similar to what you have seen in previous years' exams. And if you could give us some areas worth revising more before the exam. That's a good question. What I think we actually want to know is there anything that you do not have to revise? What I've told you not that you don't have to revise is the mining software repository part. Should I recommend then areas where you should put more effort in? Um, well, let's do a political answer to this, which is figure out which content in previous years' exams you are struggling with, and that are the areas where you should revise more. Or in the multiple choice questions, which area is the one that you're not getting right on peer-wise? That is then an area where I should revise more. But of course, I cannot say anything about what you need not to revise. Okay. Can we look into question 2, parts E and F as well? The fault localization past exam question. Okay. I assume this is question 2, parts E and F. Do you mean? Okay, so I don't know
I
which.
mean the same question that we were looking at previously, like
Oh, you
shortly.
mean question 1?
Question. Oh yeah, sorry, it's question one.
Yeah, because
The
question
other
2 doesn't
parts.
have a E. It doesn't have an F. Okay,
Yeah, sorry.
no problem. E and F. Okay. You will now try to find suspicious statements with execution dices. Describe what an execution slice is and what is an execution dice. An execution slice is basically all the statements that have been executed by a test case. Okay, so basically these are all execution slices. Now, an execution dice is when you remove an execution slice from another. Give the criterion to pick a passing test, giving a failing test to compute an execution dice. So you have a given failing test, and you want to use a passing test to create execution dice, meaning you take a failing test and remove all the statements of the execution slice for that passing test. So the criterion is that the passing test should be as similar or as close to the failing test in terms of the execution slices, but not identical. The reason if they are identical, the execution dice will be empty at the end, and you have something that is not helpful. According to the criterion, which pair of tests would you pick? Explain why. Okay, so let's go back here. So we know execution slice 4 is the failing one. And now the question is, which execution slice of the passing tests 1, 2, or 3 to take? If you look at them, you want to have the one that is having the smallest number of differences, so the Hamming distance. And that is, in this case, test 2. Because test 2 is very similar to test 4, and the only differences between test 2 and test 4 are lines 14, 15, and 16, where the results differ. Test 1, you can already see lines 3, 4, 5, 7. So 4 lines are different to test 4, and the same with 3. So you would pick test 2 as the other execution slice for the execution dice. Good. Okay, so based on the execution dice for the pair of tests you picked, which statement is likely to be faulty? Explain why. So if we compute the execution dice, so we're taking the failing test 4 and remove all statements in the other execution slice, which is test 2. When we're doing that, the only executed statement in the failed test is line 14. And that is most likely the line that contains the fault, because it is more likely that a statement that is executed by a failing test and not by any passing test, or not by a passing test, is the location of the fault or a fault. That's basically based on the observation that it is less likely that a statement that is executed by a failing as well as a passing test is likely to be the fault. This is a very elaborate explanation to just clarify the main observations. But the main point you would have to explain in the exam is that it's more likely that the statement is executed by a failing test, but not by passing tests, is likely to be location of a fault. Yes, Nishio.
A quick question about what you just answered. Following that logic in the table above,
Yeah.
Test 4, which is failing, also exists similarly to test 14, and also in line 14, I mean, in line 3, 4, 5, and 7.
Yeah.
So is the only reason we choose 14 because, like, why do we choose 14 over the other 4 lines at the top, essentially?
What do you mean with the other? Oh, so I mean the 3, 4, 5, 7. Because
Yes.
the question is, based on the execution dice for the pairs of tests you picked, which statement is likely to be faulty? So you ignore tests 1 and 3 because you have picked test 2 as it is most similar to test 4.
Oh, I see. Thank you. Thanks.
Welcome. That's the reason of Tarantula, because with the execution dice you can only take pairs or add more and more other elements there, and it's a very crude measure. And Tarantula or Oddkai takes this into a statistical approach where all available data is taken into consideration. And with the dice, it's just the beginning where you do not do the statistics, but you pick certain combinations. Okay, going through, the other question was F. You will now try to find suspicious statements with statistical fault location. Explain the Tarantula approach for computing the suspiciousness of a statement. Give the equation for the suspiciousness. Now that's a good question, because can I remember the equation for tarantula? Now I can't at the moment, because I'm not preparing for an exam. I have my head somewhere else. So basically, as soon as you have the equation, what you would do is compute the suspiciousness for all these lines. And for simplification, you can do it much simpler. The first 4 lines have the same profile, so they have to have the same suspiciousness. Any line that is not executed by a failing test has a general suspiciousness of 0. And therefore you just have to do 3 computations: 3, 4, 5, 7, 13, and 14. Correct me if I'm wrong, because all of you should now know the equation. If you want, I can come back at the end to look into the actual equation to check that I said everything is correct. But I think that's the answer for this now. Computing tarantula suspicious. Yeah.
Sorry.
Yeah, go ahead, Hassan.
On that note, so I think like all the suspiciousness for the tests, like for statement 3 to 7 and statement 14 is the same, because they are executed by one failing and one passing,
Yeah.
and those have the highest suspiciousness.
Okay.
Right.
Well, I can very quickly look into the data. So, okay. So basically, the tarantula suspiciousness is the number of failed tests that execute statement divided by the total number of failed tests, divided by the number of passing tests that a statement is executed. So I'm going to show you basically the solution here. That is this one. Okay, so here you have the equation, and if I would have thought a little bit more, I would have come to that conclusion. So basically, that top term, the number of failed tests divided by the number of totally failed of failing tests. That's an interesting one because we have just one failing test, so it's either 0 or 1. So if a statement is not part of any failing test, it has to be 0, and because otherwise we have only for one failing test, it's 1. And you're right, the lines 3, 4, 5, 7, and 14, because they have exactly the same profile, not the same profile, but the same numbers of failing and passing tests. The computation is the same. And only line 13 is different. And as you can see, this is probably the most complicated computation you will encounter in the exam, and I'm able to do that without a calculator, because we're just computing with the fractions. Okay. So in the end, 3, 4, 5, 7, 14 are 3 quarters, and 13 is half. Then the next question is, which statement is most likely to contain a fault? And here we are getting the result. Now that's, of course, that is not right. Statement 13 in this example, because it's a half, and when the others are 0.75. So this is an outdated reference solution. So if you look at this, 3 divided by 4 is 0.75, and 13 is only 0.5. So the lines 3, 4, 5, 7, and 14 are of the same suspiciousness. And you can see that with 3, 4, 5, 7, and 14, it's the same profile. Okay, and line 13 is less suspicious because it has been more often executed by a passing test. All right. Follow-up question to this?
Thank you.
Now looking at two new questions on the discussion forum. I just looked at Moodle just like 10 minutes. Let me check. I have 200 posts. Yeah, these new highlights I think are not necessarily. Okay, I can share this directly. Zoom and share. They actually appeared just before I started the Zoom session. So that's one question. For the exam, are we expected to remember the specific commands and syntax for tools like Make, Maven, Gradle, gconf, gprof, and other tools? Or is it more important to understand how they work and be able to compare their concept and usage? It's the secondary part. I cannot expect that you know all command line arguments for all the tools. So you do not have you would not have to write a command line, but if I give you a command line, let's say without any kind of trick question, you should be able to understand what it does. And with gconf, gprof, I don't think that there is any command line that I would ask. So it's more like the for Maven and Gradle, the command line, nah, it's not important. The only one that would be important to understand on the command line would be make, because that would be when there's a question about how different sub projects are integrated. So it would be specific to the sub project because then it's executed over the command line. And the concept that you should be able to remember on make is that the variables inside a make file can be overwritten on the command line. But anything else you don't need to understand from, or you don't need to remember. You will not be asked to write a command line. Okay. gprof structured profile. Okay. Explain how to interpret the gprof structured profile in your slides from week 6, please. Okay. The gprof structured profile is a bit complicated on how this is actually put together. Each one of these entries is a function that is invoked. Anything that is listed above are the functions that invoke that method of the function of interest, and everything that follows are those functions that are invoked by that specific function. Let's look at encode. Encode is invoked from main, and encode invokes all these 9 following functions. They are also numbered through. So in the called column, you have the number of times the function of interest calls the other function expressed as a ratio of how many invocations of the total invocations are coming from this function. So encode invokes string scat, which is the string concatenation, 28,000 times out of 47,000 times overall. And this is the same information that follows. So what you can extract from that is that there are almost 20,000 invocations of string scat coming from somewhere else. So you would have to look at that profile then there. Then the percentage of time. So the percentage of time basically says how much time is spent in those functions. And then it is that's the percentage, and then the actual time spent in itself and spent in its children. So by invocation of encode, that collects 70% of the time, and basically 0.0 is a microsecond is spent in encode itself, and 0.03 seconds is part of all the children that are invoked by encode. Okay. I hope that clarifies that. Follow-up question? If that person is here? Doesn't seem to be a follow-up question. Let's go to the questions again. And I think that is something I have answered with McCabe. Yes. All right. Let's go to the chat. Are there any explanation that must be given for the multiple choice question, or is it just selecting the right answer? It's just selecting the right answer. It's 10 questions, 10% of the marks. And that means you have to be able to finish it within 10 minutes. Do not write any kind of explanation. Just say which is the right answer. Okay. Is there any non-political hint that you can give us for the exam? I would have to look at the exam now, because the exam exists since January. Well, the multiple choice question covers the whole breadth of the part. And the exam questions 2 and 3, all of them cover multiple topics. So no, I can't give you any content more specific there. Let me go back to what I gave in the actual lecture. Just have to find it. Just a moment. Was it in week 10? No. Just a moment. I'm back. I'm still looking for this slide. Could be that I actually did not give that slide during the lecture. I have to go back 1 year. Just a moment. Okay, so I'm going to reuse the slides that I had in the past, the year before, and I'm going to talk to you what's different. So one thing that has changed is previous year we didn't have multiple choice questions. So your question with this non-political answer is, okay, what is relevant? So what we covered is managing changes, version control, build system, software testing, content integration, profiling, fault localization, software measurement, technical depth, code reviews. Did we cover clone detection this year? I think I skipped it, right? And style checking, static analysis. What is not relevant? Yes, the mining repository is covered by coursework. And basically that's the only topic that I can really exclude. If I'm looking at all the topics, what you really so what I would recommend is with the revision, in particular for the second part, is the later parts of where I made the connections to earlier parts. Because at the beginning, the teaching of the content was much more like, okay, so we're looking at managing changes and the version control, and then suddenly build systems, and then software testing, and then continuous innovation. And only at the very end, when we had code review, suddenly all these pieces were coming together, and there were dependencies between. So, for example, in code review, these days you would put that in cooperation with the continuous integration. And for the continuous integration, you need to build systems. And of course, everything is in a repository. So if the version control system, then you have also as part of the code reviews the bots that would say, well, where's the technical depth with SonarQube? That is dependent on the software measurement. And also, when you think about the fault localization, that is dependent on the profiling. Without profiling, you cannot do fault localization. And you would also use the information of profiling, what is covered, the coverage information, as part of the software measurement in those bots or in the continuous integration, where you usually see, or in SonarQube, which lines have been covered and what is the coverage that needs to be improved. And then the static analysis part, where we focus on, okay, well, we have the underlying technology, how to do this kind of analysis, but then we were discussing Spotbox and how you could feed that into the code review part. All these static analysis tools would all fit into the code review part. So if you look at it, all these topics come together in the end as this automated code reviews part. Okay. Oh, I just remembered one thing that you don't have to take into consideration is all the content that I had this year in discussing the impact of generative AI. For example, this very small example of how you could plug in an LLM into your continuous integration commit hooks that you could very simply create a code review bot with an LLM. So we're not having anything that you have to go into any kind of detail in that respect. Anything that I said about LLMs and generative AI is not in the exam. So finally, I found a non-political good answer for this. Okay. Any follow-up question? Okay, so they are. Does the up-to-date task in AND mean that AND supports incrementality? What's the up-to-date task in AND? Okay. So that task we haven't covered in the lecture at all. So if you haven't heard about it in this session, then you do not need to know this in the exam. Just looking at the description. So the question was actually, does the up-to-date task mean that AND supports incrementality? No. It's just capturing the state of a task. So the incrementality decides on what needs to be executed. So the incrementality in that respect is in and anyway. Okay, so next question. Is the exam going to be on paper? Yes, it's a pen and paper exam. You do not have any other way. I mean, in an individual-related situation, I don't think there would be something that would be different. Okay, follow-up question. I just now went through all those questions. Okay, doesn't seem to be the case. There was one of the things with, will UCL have free partner to exit? I have no idea. That's a technical question that I can't answer. I wouldn't assume not. You would have to answer that the central UCL exams office. Okay, I'm gonna close this. So, do we need to know the different program spectra by heart? Let's say the majority, in the sense of that you can extract them. So you have these two streams, basically the hit spectra and the count spectra. So the hit spectra only checks whether something is there or not. And what can you count? It's basically, yeah, the statements, paths, decision trees, and so on, and or capturing the traces. So the majority of the spectra you can extract again from this idea how these spectra have been assembled and what can you observe during the execution. Okay, so there was also this question from the very first question on Moodle to go through static analysis and the control flow graph. I'm going to go quickly through a few things. Let me share the PowerPoint, so I hope you can see it. So that's basically static analysis. We had the example of the Fibonacci part and so on. This is not important at the moment. Again, so here we had this ChatGPT exercise that is not part of the exam. So we are using data flow analysis. And the first thing was, okay, the control flow graphs, because control flow graphs are essential to whatever we're doing, because the first time we encountered the control flow graphs was during profiling. And control flow graphs are very much dependent also on the situation when they are used. The general idea is that our control flow graph consists of the basic blocks and how the execution of these basic blocks proceeds. Now, a basic block must have a single entrance and a single exit and no variation of execution in between. So all the statements inside a basic block must be executed always in the same sequence. And the edges between the control flow are then showing in which order those basic blocks are executed. Now, having the basic blocks, the idea there is that you cannot have like a single edge connecting two basic blocks, because then you would have no branching and you could merge those two basic blocks together. So in this example, what we are having is this situation. We have a basic blocks, lines 6, 7, 8, and 9, because these are the four statements that always have to be executed at the same time. Line 4, the executable elements is the assignment to F0 and F1. That's one basic block. Then you have the branching point where the check for n larger than 1 is executed. That is in line 5. You have the return statement that is executed, and you have two situations here in which you have a single incoming edge to a basic block, which is basic block 1 and basic block 3. Now, in basic block 1, that is because it's connected to the entry, and the entry is never merged with the next basic block. And you have the basic block number 3, which has one incoming and one outgoing edge, but the incoming edge comes from a branching point. And this similar situation is in statement 4, where you have a single edge going out and a single edge coming in. The incoming edge comes from a branching point, and the outgoing edge goes to exit, and therefore they are never merged. So you cannot expand blocks 1 and 4, and of course you cannot expand blocks 1, 3, and 4, and you cannot expand block 2, the condition checking, because it has multiple entries and multiple exits. And that's how you construct these control flow graphs. Basically, at any branching point, you are connecting these basic blocks. Yes, is there a question? Somebody wanted to say something?
Yeah. So the previous example that we just covered, that's reused in, I think, static analysis, where we we try to reach the fixed point um, by looking at the predecessors and what the output set. Yeah, basically this bit. In the for basic block 4, does basic block 3 become the predecessor since it has like an indirect so basic block 3 I mean it can go to the while, I mean there's an edge from 3 to 2,
Yeah,
and then there is an edge from while to basic block 4.
yeah.
Does that make then does that mean that we need to consider the outset of basic block 3 when we are calculating the inset for basic block 4?
No. There's no connection between basic block 3 and basic block 4. So the computation for the incoming set cannot come directly from basic block 3.
Okay. But we consider basic block 1 for the calculation of incoming set for 4 as well, right? I think in the example.
No, no. Okay,
Okay.
so if we're looking at this, this is how to do. You basically go back to the equation,
Yeah.
okay? And they exactly say how you are computing these, okay? So the incoming set is all predecessors. And if we are looking at this, that means the predecessor of basic block 4 is only one. That's the basic block 2. And basic block 2, however, has two predecessors, basic block 1 and basic block 3. Okay, so basic block 3 has one predecessor, which is basic block 2. Now there we have the cycle, which makes the fixed point iteration like a requirement. You repeat the computation until none of the sets change any longer. So you've reached a fixed point of the results in the data sets.
If there wasn't a cycle, we wouldn't need to do the fixed point calculation at all.
Yes. So if you have code that has no loop, then there's no need for fixed point iteration.
Yeah. And since basic block 3 does not have a direct edge to 4, it is not its predecessor. Because I think in the table that we create, the one for basic block, yeah, I mean after the I think 21. So set
Animations.
4.
Yeah.
Okay.
So that's the start, and that's why we're doing this top element initialization. And I think I have to run the animation to make that clearer. Slideshow, play from current slide. Can you still see this? Can you see the animation?
Yeah.
Okay, so basically it is. Okay, we start here. We start our computation. We compute the inset for basic block 0, which is the entry, and the out one. Then we continue to 1, compute the inset, which comes from basic block 0. The outset, which is nF0F1. So we are at 2. Now 2 has two predecessors, block 1 and block 3. So we compute the union, now the intersection, in this case, the intersection of the outsets from block 1 and block 3. And then the intersection of nF0F1 with the top element is nF0F1. Then the outset for block 2 is straightforward. Now we have block 3. Block 3 has one predecessor, so basically it just needs the copying the outset from block 2. and creates a new outset, which is NF, F0, F1. So we're now at block 4. Block 4 has one single predecessor, which is block 2. So we just copy the outset of block 2 into the inset from block 4, which is NF0, F1. And you can already see there's no impact of block 3 at all, because block 4 is not connected to block 3.
Yeah.
And the rest is straightforward. And in the second run, we are seeing that we have reached a fixed point because none of the computation has changed.
Got it. Yeah.
Is that clarifying this?
Yeah, I think I was just confused at how the outset of S4 was being created if there
outset.
was but since 3 had like an indirect like it seemed like it was an indirect predecessor, but yeah, it makes sense.
Yes, it's the problem of the recursion.
Yeah.
So, I mean, all the information is in the end indirect. That's why we are doing the data flow analysis. Because the information from block 1 is over multiple steps indirectly reaching basic block 4 and basic block, in the end of block 5.
Yeah, got it.
Okay.
Okay.
Good. And that, I think, explains the main parts of the static analysis. Let's go back to the chat. Okay, is this section recorded that we can review later? No, it hasn't been recorded, because that gives so recording is always problematic when students are able to ask questions. That's the reason why these sessions are not recorded. For creating a control flow diagram, can I use line numbers instead of writing the whole code? Oh, you mean on the exam? Yeah, that's just fine. And then somebody had to go to leave. Okay. Any follow-up question? Last chance.
Just a quick questions regarding the control flow graph.
Yes.
So in that example, after we declaring F0 and F1, that's a while loop, right? So what if that's a if? So do we separate two blocks if there's a if?
You mean in... Okay, so let me share the screen again, sorry. Share. So that we can... Okay, so where do you mean would be an if statement?
Yeah, so if we just hypothetically, we just change while n is greater than 1 to if n is greater than 1, do we need
Okay.
to still separate block 1, block 2, or that should be in
Oh,
one
yes,
block?
because block 2 is still a branching point, because if that would be an if statement, from block 2, you can still reach block 3 or block 4 directly, depending on the outcome of the if statement. So the change would be then that you do not have a connection, not an edge from block end of block 3 to the entrance of block 2, because then you would have the connection from the end of block 3 to the entry of block 4. Because the block 3 would be executed if n is larger than 1, but only once. But
Okay, makes sense.
the basic block structure would not change. Okay.
Yeah, okay, makes sense. Thank you.
Welcome.
Professor, sorry.
Yes, go ahead.
One question is so the output of tree is the input set for second block as well. So won't it consider an F node F1?
Sorry, don't get the question. Can you repeat?
Yes, for the second run,
Yeah.
the second block will have the output of the third block as well.
Yes. In
So
both runs, the computation is the same. So in the first run, let's go there. You have that the outset of block 3 at that point is still the top element when you compute the inset of the block 2. So you take the outset from block 1 and the outset of block 3 and create the intersection. And you do the same in the second run. Okay, so the second run, we're here, and again, you do the intersection of the outset of block 1 and the outset of block 3. Now, the result of that computation does not change the inset. And no other set is changed. So we've reached a fixed point, which we know when we have computed all the sets. None of the sets has changed. Does that answer your question?
Yes, yes, got it. Thank you.
You're welcome. Back to the chat. Are pencils allowed in the exam? Yes, I believe so. I've seen pencils being used before. So the benefit of a pencil is you could erase it again. Yeah. You are not allowed to write in a different color like green or red. That's banned. I think you are supposed to write in black or blue. I'm not so sure. Look up the instructions on what you're allowed to have in an exam. Okay. Anything else? Last chance? Other than that, good luck with the exam. And good luck with all the other exams you have too. I hope it's not too complicated. And particularly, I also hope that it's not too easy. I hope that it's fair. Because it is in this large situation of the Excel, and I think it's the first exam that you're going to have, is have you been instructed what to do when you think there is a problem in the exam? So I believe okay, Hasan, have you been instructed or have you not been?
No.
Okay. So I believe if you think there is a problem on the exam, there shouldn't be because these have been multiple times been checked. The instructions, I think you have a special piece of paper, or you can get the special piece of paper where you take the note of that. Or you would have to write it on the exam that you think there's a problem, and then assume what the question should be and answer that question. So if you think there's a problem, then you must specify what you assume should be the right question and answer that one. Now, be very, very careful at that point, because if there is no problem and you make an assumption in the deviation and therefore you answer something wrongly, you will be marked on what was really asked, not what you assumed. Okay? Because of the situation that all exams are together at the same time in the exam, there is no possibility to get any question answered during the exam time. Okay? I will not be there. So no actual academic is supposed to be at the Excel, because there's no process for announcing anything during the time or answering any kind of questions. Okay. All right. Good luck with the exam. And then I think the majority of you I will see during the induction for the group projects. And other than that, enjoy the rest of the day. Don't be afraid of the exam period, and good luck with everything. Bye-bye.